Perfect. And this is lecture 14 of high dimensional probability, which actually marks 1 month since we started this course. And yeah, we are roughly 30% through with this. Thank you so much, everyone who is doing homework and who is coming to these classes in person. So if you are watching us online, please consider also coming in person and interact, just ask questions and interrupt me during the class. That's most valuable. And if you're doing homework, great. I think that's a great investment of your time eventually. Good. So we will now finish a stretch of 4 lectures that are foundational, which is on theoretical foundations. And then we'll have 4 or 5 lectures on applications to data science. And then again, there'll be a stretch of foundations and applications. So bear with me for this one last class where we just set up the class of random variables, the standard class that is popular in data science. And that is what we introduced last time, last maybe 2 classes previously.
We don't see presentation.
Oh yeah.
I don't see.
Yeah. My bad. Share screen, of course. Thank you for noticing that. Share content screen. Okay, now you do, right?
Yes.
Perfect. Okay. Last couple of classes, we introduced a standard class of random variables, standard popular in data science. And the reason being that if you want to, let's say, guarantee that your algorithm works for any kind of data, if you allow totally, completely, just want to guarantee for anything at all, well, that's rare that the algorithm will work with even with the worst possible data. So usually you say the algorithm works with good data. And what is good data? Well, there are different versions of it, but one thing that you can say is that, well, it's a data sampled from normal distribution. True, it usually is a good data, and statisticians would probably buy it, but it's very restrictive, just normal distribution, just one class. And so we're trying to build a class that is, on the one hand, general enough. For example, it would contain Bernoulli random variables, very, very discrete, and normal, very, very continuous. So a very wide class, but on the other hand, it would inherit as much good properties from the normal distribution as we like. And this is called Sub-gaussian random variables. So X, random variable X, is Sub-gaussian. If its tails are decaying as fast as the Gaussian tails, or maybe even faster. Something like this. So more formally, this happens for this has to happen for all the tails. So the tail behavior is like this. And K is some parameter, some number. So if there exists a K, so that this holds. This is one way to define it, but there are many ways actually. So this is only one of the ways with K1. And we put like 4 or 5 equivalent ways of defining this, and all of them can be used. You can use them whenever you feel convenient. The LP norm, which is basically the piece moment, but normalized this way. The LP norm, they always grow for any random variable, and they grow to the L infinity norm, which is the hard maximum, like supremum, and it's infinity, so they grow to infinity, but the question is how. So for Sub-gaussian, they grow like this, just like a root of P. Another equivalent way of saying this is that e to the x squared up to some constant is, let's say, smaller than 2. And the fourth way this happens, this is only valid if for mean zero random variables, is that the moment generating function is bounded like this. You don't have to memorize all this, but just to know that Sub-Gaussian properties inherit much of the Gaussian behavior. Good. So this was our kind of definition of Sub-Gaussian with equivalent, like 4 equivalent definitions of Sub-Gaussian. Sub-Gaussian property is not only qualitative, yes or no, like Sub-Gaussian or not Sub-Gaussian, but it's also quantitative, how Sub-Gaussian it is. And that is given by these constants, K1, K2, K3, K4. In fact, all of them are equivalent. So we notice that too. All Ki's are equivalent. Formally, it means that they're within an absolute constant factor from each other. So, okay, I may be cheating here, but something like this is true, like say 4 times K1. And for any pair, you can do something like that. All of these constants are equivalent. And some of them define a norm, and we just picked the third one. This defines a norm. So the best K3, the smallest K3 is a norm that we define this way, Sub-Gaussian norm. So it is homogeneous, it satisfies triangle inequality, all of that. It defines almost like a distance on random variables. Good, that's what we did. We introduced Sub-Gaussian random variables qualitatively, then quantitatively. And here we go. Any questions before we continue with this for this last class today? No, you're good. Perfect. Okay. In the homework, the current homework, we will notice that the Sub-Gaussian norm, although it could be a little bit mysterious, what it's really saying. So the Sub-Gaussian norm is kind of, it captures this, well, in the ideal world, it would be like standard deviation, something like that. It would be, it's like standard deviation. It also measures the spread, but it measures much more. It has a much more complex task, so to speak. So the Sub-Gaussian norm is actually larger usually than standard deviation. It's harder to control more things, so it's going to be fatter, larger. But if you know nothing about random variable in the beginning, you should assume like, okay, in your brain, it's like, okay, it's like standard deviation, only a little bit maybe larger. Examples. Trivial examples. Normal distribution, of course, is Sub-Gaussian. Clear? So examples of Sub-Gaussian distributions. Normal distribution is Sub-Gaussian. Bernoulli distribution for any parameter p Sub-Gaussian. Why is that? What do you think? Why would Bernoulli? Bernoulli is very far from Gaussian, right? It's just 2 points. How can?
Because it's bounded?
Bounded, yeah, exactly. Bounded, and then what? Then which of the properties is the easiest to check, for example, for the bounded?
Tails.
Hmm?
Tails, like the first property.
Tails, yeah, the first property there. Tails, the tails of the bound are like this. There's something and then bim, and there is no tail at all. So of course they decay exponentially faster, just nothing after some point, 0. Tails. Also, this is very easy to check for the bounded as well, right? If x, like Bernoulli, if x is bounded by 1, then of course expected value of x to any power will be bounded by 1. So this is bounded by 1, then of course it's smaller than root p. Yeah, so that's trivial. Uniform distribution on let's say interval 0, 1 takes values with the same probability within 0 1, same reason, right? It's still bounded, just like Bernoulli, so it's obvious that it is Sub-Gaussian. And we already noticed that, in fact, this argument is pretty general. So any bounded random variable is Sub-Gaussian. So for normal Bernoulli uniform, the Sub-Gaussian norm is a constant. Can't remember exactly what constant it is, 2 or maybe log 2 or something, but it's an absolute constant, less than 4 definitely. Just for the reasons that we described. And any bounded random variable, let's say if x has a hard bound, almost sure bound, then the Sub-Gaussian norm would be bounded by that bound. Maybe absolute constant is there, but just a little thing to check. Good. Perfect. So these are examples. A lot of discrete examples covered, a lot of continuous examples covered. Very, very good class. Okay. So like I mentioned that the Sub-Gaussian norm is kind of a proxy for the standard deviation. So the square of it is kind of a variance proxy, let's call it this way. Which means that I can't rigorously say that it's comparable to the variance, because of course it captures more. But in many ways it behaves like the variance would. For example, the variance of the sum of independent random variables always equals the sum of the variances. You know that, right? Variance of sum of variances for independent. Perfect. And now we'll just notice that a similar phenomenon holds for the Sub-Gaussian norm. If xi's are independent, mean 0, because variance, it's not quite, the variance actually subtracts the mean, and Sub-Gaussian norm doesn't subtract the mean, so I have to throw in mean 0. Sub-Gaussian, then the sum like this. Okay, it's Sub-Gaussian norm squared, which is like the variance. I just need one-sided bound. Like this. Some of the kind of variances, but these are Sub-Gaussian norms. We'll prove it in a second. It's like one-liner. But is it clear what is it saying, right? It's kind of it's kind of a metaphor for this. The variance of the sum is sum of variances. So Sub-Gaussian norm, the sum is Sub-Gaussian norm. Okay. Proof. So now we have to deal with the sum of Sub-Gaussian random variables, and we have a choice. We have a menu here. Which of these properties would be the easiest to use to prove this proposition? Which of these properties are more convenient for the sum of random variables? For example, this is super hard, right? If I know that one random variable x has this tail behavior, then how do you know that the sum of n of them has the same tail behavior? No way. This is very hard. Yeah, exactly. Someone is saying the right thing. So the LP norm hard. E to the x squared hard, because you have to square the sum. And you have a lot of cross terms. What do you do with them? E to the lambda x easy. right? Moment generating function of the sum equals the product of moment generating function. You just use independence. Yeah, so this will break up. E to the lambda of the sum will break up in the product and use independence like we always do. So this is exactly. So who said in the chat that it's MGF? Perfect. The fourth property. So we'll use that. The MGF. Let's compute the MGFs. Compute the moment generating function of the sum. Well, just like we said, the exponentiation of the sum factors like this. Yeah. Now we can bring expected value inside by independence. And we get this. Let me just, I'm rewriting the same thing. Product e to the lambda xi. Yes. Okay, good. And now what? What do we know about the MGF of individual random variables? Well, there are Sub-gaussian random variables, so they satisfy this bound. Bound 4. Right, so I'll just bring it down there. That's the one that we're using here. So by the Sub-gaussian property 4, each of these is e to the okay, ki lambda squared, where what's ki? All of these ki's, all of these k's, they are equivalent to each other and to the Sub-gaussian norm. Right, so ki's, I can't just say they're equal to the Sub-gaussian norms, but they are equivalent within a constant. So of course this bound holds. That's because all of them are the same. Okay. Good. Perfect. So we'll continue. Okay, this was a crucial step. Was this clear? Everything is good? Okay, because then it's easy. You just convert this back to the sum. So bring it in the common exponent. C is a common factor, lambda squared is a common factor. There is a sum of ki squared. Actually, sorry, there's just C is not there, just like that. Yeah, and then we substitute the ki here, and this is because e to the power c lambda squared, the sum of xi. Okay, so what did we do?
The last two equations should be inequalities.
Should be inequalities, right? Yeah, they should. Actually, yeah, this and this, yes. Yeah, thank you. Perfect. So what did we do? We bounded the moment generating function of this, whatever it is, like maybe this is x. Right? Moment generating function of this is bounded by what? E to the c lambda squared times something. Call this k. So we're using again the fourth property, and that means that whatever it is, x, which is a sum, its Sub-gaussian norm is bounded by this c, maybe a different constant, times k. And that's what we wanted to prove.
Could you please explain more about the last step?
Yes. So we chose in this proof to operate on the level of moment generating functions. So we're kind of, we are using this as an alternative definition for the Sub-Gaussian now. All of them are equivalent, but we're using this, okay? So in the
Yes.
last step, the last step shows that, let me do it in blue maybe. The last step shows that expected value of e to the lambda, and then there is a sum, x, is bounded by e to the lambda squared times k. Forget c for a moment, something like this. Yes? And k is this. So we proved a bound of this form. Whenever we have a bound of this form, it automatically means that the Sub-Gaussian norm of x is bounded by k, because that's an alternative definition, one of them. And then we just remember what x is, it's this sum, and what k is, and k is this, and this is what we wanted to prove. So again, our goal was to bound the Sub-Gaussian norm. And how are we going to do this? I'm going to bound the MGF, the moment generating function. If we find that the moment generating function is bounded like this, we win. That's it. Then we know that the Sub-Gaussian norm is less than this. And we did that.
Okay, thank you.
Vladislav, you're good, right? And understood?
Yes. Yeah.
Perfect. I'm glad. Anybody else? It's kind of a weird thing, but think about this proof a little bit more and you'll get it. Good. Okay. Now it happens. Now happens a very interesting thing. So Sub-Gaussian norm automatically gives us the tail behavior. It automatically gives us a Sub-Gaussian tail. So what we just did, we proved a Sub-Gaussian tail for sums of independent random variables. And that's Hoeffding's inequality. So we've actually proved Hoeffding's inequality in a more general form. Let's just record it. So this proposition, if you use proposition and property 1, which is Sub-Gaussian tail, we automatically get the general form of Hoeffding's inequality. Same assumption, if xi's are independent, mean 0, and Sub-Gaussian, then let's just think. So we have a bound on the Sub-Gaussian norm of this. So this means that we have a tail bound. 1 to n, tail bound of that thing. It's greater than t, is less than. Let's just look up what kind of tail bound. This kind of tail bound, 2e to the minus t squared divided by the Sub-Gaussian norm. So I'll just put it there. It's 2e to the minus t squared divided by the Sub-Gaussian norm of the sum. And Sub-Gaussian norm of the sum is this. Okay, maybe, sorry, let me just, for better presentation, let's do sigma square, where sigma square is the constant like this. You guys, do you understand this? No math here. We just reinterpreted this proposition in terms of the tail decay. If the Sub-Gaussian norm of this thing is bounded by something, this means that this something has this tail decay. And what do we put here? Well, we put here the Sub-Gaussian norm, and we bounded Sub-Gaussian norm by this. So that's just, If you think about this definition, that's what it says. A proposition, sorry. Yeah. Good. Now, to make it more aesthetic, let's, and I hope this will be one step that's clear. Let's put the C from sigma square into the bound. So I'll erase C from here, and I'm putting this C like here. I just want to make sigma square very clear notion like this. Okay. Okay, guys, do you understand the theorem now? How the theorem follows straight from?
May I ask a question?
Yeah, sure.
Like in the Hoeffding's inequality for Bernoulli's random variables, we like have we had right hand side free of n, and here we have sigma dependent n.
Yeah,
yeah. A bit different. No?
Yeah, thank you, Vin. It's a good thing. Let's do this. So we'll next thing we will make an example. We'll actually reprove that example for Bernoulli and make sure that it is consistent and everything is consistent there. But for now, formal statement should be clear. And if you look at the right-hand side, it should kind of maybe ring a bell in your brain. C e to the minus c t square over sigma square. That looks like normal distribution, also normal distribution, but with variance sigma squared. Right? Remember the PDF of the normal e to the minus x squared over 2 for standard normal, but generally 2 sigma squared. So what is...
okay, like we normalized the sum in the original. Okay, I get it.
We normalized like
I
one.
get it.
Yeah, but I don't want to do this next. So yeah, so we this tail looks like a tail of the normal tail, but with variance sigma squared. Yes, standard normal tail, but with variance sigma squared. What does that mean? It means that sigma square is kind of the proxy for the variance, which it is. So this is almost, so this is the tail of the normal distribution with variance sigma squared, where sigma square is the variance of the sum, which is the sum of variances, obviously. So if it was a normal distribution, the result will be obvious. This will be just the normal, just the fact that the sum is normal. What is beautiful is that we have proved it far beyond normal distribution. For Bernoulli, for example, it's also true. So we did that. So example. We already had one Hoeffding's inequality, which is for symmetric Bernoulli. Let's check that they're consistent, that it actually follows from there. So xi takes value 1 and minus 1 with probability is 1/2 each. And the form of that inequality was that, yes, like if any said, we normalized like this. And we did it because this funny normalization normalizes the variance. Now the variance is 1 of that sum. Okay, so let's check it. Let's actually apply it here. So this is let's bring root n to the right-hand side. Xi is greater than t root n. And now we apply Hoeffding's inequality, except we apply this instead of t. Not for t, but for t root n. Minus c t root n squared divided by sigma squared. Where? What is sigma squared? It's a sum of the Sub-gaussian norms The Sub-Gaussian norms are constant that we figured out. It's Bernoulli, so everything is like constant here. So we sum these constants and we get maybe Cn. Yeah. So there's n of them. So if we substitute this for sigma, we get 2e to the minus ct. So t root n squared, that's t squared n, divided by Cn. And n cancels. Wow. And then we get just some other constant, t squared, just a Gaussian tail. And that was our original Hoeffding's inequality. So we recover. The original Hoeffding's inequality, except maybe we lose a constant. There was constant 2 or something. Perfect. So we proved the original Hoeffding's inequality for Bernoulli random variables, symmetric Bernoulli. And that was very restrictive, of course. And now we have a very general Hoeffding's inequality that covers simultaneously the Bernoulli case, like this, and the normal case for which it is trivial. Very, very discrete, very, very continuous, and very good, very general inequality that you should probably know. Good. Any questions? We'll use it a lot. Okay, good. Everybody's happy with this? Perfect. General thing. Okay, perfect. There is one thing that you may not feel happy about, and I don't feel happy about. And that is that all Subgaussian distributions are good, and they're a general class, but sometimes they're not enough. And let me give you a very simple example where Subgaussian distribution is not enough. Let's say you have a Gaussian vector, just a Gaussian vector in 2 dimensions, and you would like to study, let's say, g1 squared plus g2 squared, just the norm of it. That's called the chi-square distribution. Just running the chi-square test. g1 squared plus g2 squared. Very, very natural thing. Unfortunately, it's not Subgaussian. Well, even g1 squared is not Subgaussian. Even g squared is not Subgaussian. If g is Subgaussian, g squared is not Subgaussian. And that is, well, why would that be true? Let's see. For example, here, if instead of x, I have x squared, let's say, put x squared, then everything kind of squares, and instead of root p, we'll have p. And so the behavior is destroyed. So the squaring the thing doesn't work. And if I put here square, I would have, instead of t squared, I'll have t. So the tail will be heavier. And everything will actually collapse. And so what do? Like, you want to run chi-square tests. You want to study the norms of vectors. It's very, very natural. But the Subgaussian doesn't cover it. Is the problem clear? Yeah. Okay, so what people do? What do people do? They just say, okay, fine. Subgaussian doesn't cover it. Let's just make a class that covers it. That's it. We're not having root p. We have p here. Fine, let's define it this way. It will be a different class. We have a heavier tail. Let's define a heavier tail, and then prove that all these properties are equivalent, the new ones. So that's what people do, and that is very natural. And you should probably know that something like this happens. So we'll make one example of this. It's called sub-exponential distributions. So, okay, so here's a problem. Even if x is Subgaussian, it does not imply that x squared, let's say, is Subgaussian. And the example is the normal distribution. If you square the normal distribution, you get g squared. Let's look at the tails. G squared is greater than t, Let's check the tails. So take the square root of both sides. And this, we know how this behaves. This behaves like a Gaussian tail, but with square root of t instead of t. So this is e to the minus t over 2. Which is bad, because this is exponential tail, not Gaussian, not like t squared tail. Exponential tail. It's heavier. So it's heavier like this than anything like minus ct squared, for example. So it's heavier, larger than the Gaussian tail. It's not g squared is not Sub-gaussian. And we have that problem all the time. So let's just once and for all, in this end of this streak of 4 lectures, the foundation lectures, just handle that problem, and then you will see how to handle it in a general case. Okay, so the fix is, if this is what you're dealing with, if this is a heavier tail, let's redefine everything with that tail. It will be a different class, a larger class. Who cares? Let's do it. So the fix to this problem solution is to define a new class, to define, let's say, new class, exponential, let's call it sub-exponential distributions. And let me go back and just borrow the Sub-gaussian class here, copy, and make the necessary adjustments. So this becomes sub-exponential. Paste. Okay, here we go. It will be like a proposition. Let's see. Again, a proposition, then that's x is not Gaussian anymore. Go away. Sub-exponential. If the following one of the properties hold, and we will skip the proof that they're all equivalent, but the proof is the same. So first, okay, let's go and fix it. This, okay, the tail, well, we know the tail has to have t in it and not t squared. So I just remove t and I remove the square from k1. Okay, now they're normalized the same way. Second property, LP norm is bounded by a root p. Well, if you just imagine, if you square the Gaussian, things would square, and so instead of root p, you should expect p. So let's just remove the root from there and get p. Third property. This is less than 2. This is a little harder to guess what will happen here, but in this case we don't square x. Okay. So I just remove the square again, like this, but I want to keep absolute value so that I'm actually looking with positive. And the smallest k3 is called Sub-gaussian norm. And instead of psi1, psi2, I put psi1. That was actually the reason why it was index 2 there. And it's called Sub-exponential norm. Good. So far, so good. Okay. The only surprise here comes in the fourth property. Right? If we didn't have enough sleep or coffee in the morning, we would just say, okay, the correct fix would be to remove the squares here. It should be not lambda square, but lambda. Wrong. Why wrong? Because this is MGF, the moment generating function. And remember what moment generating function generates? Moments. Right? So the first moment, which we assumed is 0, is the derivative of the moment generating function. It generates moments by differentiating. So this expected value of x is 0 means that the moment generating function has to be like this. And if I remove lambda here, that means that e to the lambda is something like this. It means that the moment generating function would be like that, and the moment would not be 0. So that's definitely a wrong idea to do that. It would never happen. Okay, so since we know that the expected value is 0 already, it would make sense to leave the same bound. However, if you try to prove this bound, you will not be able to prove it, obviously, because otherwise you would have Sub-gaussian class. What you would be doing instead, let me just make a little kind of a metaphor here. So let me try to prove this kind of e to the lambda x. I would have to have the integral to integrate e to the lambda little x against the density, and the density will look like something like e to the ct, not the Gaussian density, but something like exponential density here in this class. So cx, sorry, cx. That's our variable here. And see what happened. What happens here? Now I can't do this for any lambda. If these terms oppose each other, they fight each other. And so if lambda is too large, that will become infinity. If lambda is greater than c, it will only be finite if lambda is less than c. So the moment generating function would not even exist for everywhere for Sub-gaussians, for sub-exponentials. Okay, so that's our problem. That for sub-exponential distribution, it becomes a little heavy, so that moment generating function, we can't guarantee its existence even everywhere. Around 0, yes, we can for small. And that is what will happen here. So here is a fix. We still have the same bound, but this bound will only hold in the neighborhood of 0. Okay. This is now the correct statement. This will be the fix. And we will actually skip the proof. It's in the book, or maybe it's as an exercise in the book, but it's really all of the same steps. So we'll not bore you to death with this. But is the idea clear? Yeah. All of these properties generalized from Sub-gaussian to Sub-exponential, except the last one. And the last one is still the same, but now in the neighborhood. If you ever need more than that, if you have, I don't know, if you want to look at random variables that behave even worse, maybe minus root t instead of t, then you know how to do the fixes. Yeah. Root t here, p square here. You got it, right? So maybe root here, and this I can't remember what to do with this. Any questions about this fix? Cool. Okay, examples. First, any Sub-gaussian random variable is automatically sub-exponential. For example, the normal distribution. This is a triviality, right? Sub-exponential is just heavier. Well, of course, if we have Sub-Gaussian, then the growth is like root p, which is slower than p. So of course, one implies the other. B. Any Sub-Gaussian squared any Sub-Gaussian squared. So for example, g squared, that would be a sub-exponential random variable too. Here's basically the proof. We did it for normal, but could be done for general. Right? You square a sub-exponential, you bring the root in the other side, and you do this, and it's sub-exponential. So that's easy. And that actually shows that the best constant, like if you square it, the sub-exponential norm is the same as Sub-Gaussian norm of the original squared. Check this formally, but that's exactly what this argument produces. Good. Now the genuinely new examples, the exponential distribution. The exponential distribution is not Sub-Gaussian, but is sub-exponential. Actually, guys, do you remember this? The exponential distribution. Have you studied it before? Exponential distribution. It's one of these standard probability distributions, like normal and Poisson and geometric and exponential. Yeah. Okay. Yep. Perfect. Okay. Who knows what is used for? Well, give me an example in the real world what exponential is actually the distribution of choice to model something. No, I don't remember. Okay. Continuous, yeah, okay. It is a continuous version of the geometric distribution, correct? Okay, so what is geometric distribution used for? To model. Where do we ever see a geometric distribution? What was the example that was used to motivate them? Yeah, waiting times, exactly. Yeah, geometric distribution. You wait, you flip the coins until the first head arrives. How many flips you need? Geometric. If you do something, you perform continual experiments until the first success, and that's how many times you need to perform the experiment. Geometric. Exponential is a continuous version of that. So,
so it's like the length of the phone call before it terminates.
Exactly, the length of the phone call.
I'm starting to remember something.
Yeah, perfect. Yes, this is it. Length of phone call to terminate. More, I guess, well, because we get tired by waiting too long on the phone call, so that it's kind of a little bit not exponential. But what is a good example is the length of the wait time for the call. Let's say you're in a police station and you're waiting for the first call. How long do you have to wait? So the interval between successive calls, emergency calls, or whatever, airstrikes, that's exponential distribution. Yes. Wait times, yeah, Daniel says the wait time before the bus arrives, so kind of exponential, because if you wait for too long, then maybe there are other factors, but yeah, all these wait times. So exponential distribution. It is actually the best way to define it. It's something like this. It's a tails. That's how you define exponential random variable. So it's automatically exponential, sub-exponential, sorry. Okay. So it's maybe important to note that this is not Sub-Gaussian, but it is sub-exponential. So that's one example where we need that class. Another example is Poisson distribution. its tails are some, I wish I remember this homework example, sub-exponential, something like t to the minus t. I can't remember exactly, but so it's e to the minus t. Yeah, so it's better. They're a little better than e to the minus t for large t. So they're better, a little better than exponential, but they're heavier than e to the minus t squared. So Poisson is not Sub-Gaussian, but it is sub-exponential. So it's one more practical example of where you need that. Okay, good. Okay, perfect. So we fixed the class now. And now the question is, okay, we want the tail behavior. We want something like this. That's our, it's Hoeffding's inequality, let's say. Can we expect that? Can we expect something like this? We move it around, copy, paste. And the question is, does Hoeffding's inequality or something like that hold for sub-exponential distributions? Does it hold for exponential distribution for this one, for example? What do you think? Is there a chance? It's an easy question. Is there a chance? How we're saying, how can we expect that Hoeffding's inequality holds with Sub-Gaussian tail, where each random variable does not have Sub-Gaussian tail? Right? We're trying to produce something better than reality. Of course, it cannot happen. Okay?
Yeah, but maybe it holds for a different kind of for t, for example, not t squared.
Yeah. True. Yes. Okay. My question was too kind of blunt, I guess. Yeah, exactly this, like t squared. No way, right? Maybe for t it does hold. Yeah. Okay. Sorry. Yeah. Of course you already assumed that the same fix would fix the Hoeffding's inequality and we would replace it with t. No. I'm just asking about this. Okay. So no. Now, will it hold if we replace it with t? That's a different question. We would like to have t squared. Why? And we kind of hope, maybe, even though it's not true, we're trying to hope that this is true. Why? Because we know the central limit theorem holds anyway. Because in the limit, the things will become kind of normal. And the normal distribution does have this tail. So something like that should happen. But on the other hand, it cannot happen because even for t equal 1, even for n equal 1, just one random variable, we have an abstraction. We have e to the minus, the tail would be ct over k, so exponential tail, where k is the sub-exponential norm. So that's not true. Too heavy. The tail is too heavy. Okay, so now the beautiful positive answer to this is this. The tail is too heavy, so we cannot have it. However, it turns out, very surprisingly, that this is the only abstraction. So the sum of random variables, the sum of sub-exponential random variables behaves like this. So this is true, except there is this abstraction for n equal 1, except just one single terms can be too heavy, not collectively. So collectively, they will be good, but one single terms can be abstraction. And here is how we can state this result, which is very useful. It's called Bernstein's inequality. You prove it exactly the same way as we did all this MGF. So Bernstein's inequality. So if xi's are independent, mean 0, and sub-exponential, then the tail behavior is 2e to the minus, and then there will be two terms, whichever wins. So I'll put the minimum of them, and the minimum indicates, you know, the smaller the term, the worse it is, right? Because you would like to have something large here. E to the minus something large is something small. That's why. So minimum is picking the winning term, t square over sigma square. This is a great one, great term, up to a constant. So c times great term. And the other term will be this. The term that comes from just one, the bad tail that comes from just one term, t over k. So sigma square is just like before, the sum, in this case, sub-exponential squared, variance proxy. And k will be this I1 norm, the worst of them. So I'll put the maximum. So the right-hand side may be a little complicated, but you should think of this as a mixture of two tails. The Sub-gaussian tail, the Gaussian tail, and exponential tail. The Gaussian tail is a product of central limit theorem in the back of our minds. Right? So the central limit theorem works, and it should produce something like a Gaussian tail. Great, we love it. The exponential tail is worse, but it's only produced by the contributions of by single term in the sum. It's not a collective work. It's just to make sure that the tail of one of each single random variable is okay. And usually it doesn't cause any problems. Is this formal statement clear? Yeah, perfect. Prove absolutely the same way. The MGF method as before. Let me do this very, very quickly, and then we'll just finish it. The same as in Chernoff, as in Hoeffding's inequality. So you look at the sum of random variables, and you want to bound the tail. So you multiply both sides by lambda and exponentiate. Then apply Markov's inequality. To the lambda t, this is by Markov. And then remember that S is the sum. Xi, so it's the moment generating function factors. So you have the expected value of the product, which you can interchange. So product of expectations of e to the lambda xi's. Like this. This is the common beginning to everything, to Chernoff's, to Hoeffding's inequality, to general, to this one, Bernstein's. And what it does is it reduces the problem to bounding the moment generating function for each single individual random variable, which is easy. And how do we do that? Well, we do it by definition. This is what we did with Hoeffding's. So this, if without any restriction, that would be sub-exponential distribution, right? So the MGF is bounded by this. So we bound it by e to the lambda, whatever, like c lambda square or something. I guess lambda squared xi squared like this by this property 4. Only with one important difference, that this bound doesn't hold for any lambda. So we only can do this for small lambda. That's because of this restriction. This is the only difference between the previous argument and this. We can't run this for any lambda. Then in the end, when we optimize in lambda, remember we do this, then lambda is arbitrary number, arbitrary parameters, we can optimize in lambda. And when we optimized in lambda before, we didn't have any restriction. We just choose the best one and we get Sub-Gaussian tail. Now we have restriction. So how do we optimize with restrictions? You take the derivative and then you check the boundary conditions, right? And the boundary condition produces this factor. So this is the product of the boundary condition later. So you'll get QED this way. Maybe you can check it yourself. So same proof, only with this little wrinkle that lambda is not free anymore, and the boundary condition imposes this restriction. That's it. Yeah, that's it. So we finished this streak of 4 lectures on foundations. We have now great ways to find concentration inequalities, like tail behavior for anything, like for Sub-Gaussian, for Sub-exponential, for the square of them, anything. And we will then start 4 or 5 classes on applications. First on dimension reduction, data compression, and then on kernel methods, I think, and then something else. Oh yeah, on graph clustering, community detection. So yeah, you'll love it. Any questions? Good. Anything? Okay, we'll stop recording now.